going to continue with chapter 5. Today, we're going to be looking at section 5.4, where we're going to reintroduce exponential and logarithmic functions, and we're going to see how to not only take derivatives of them, but also how to take integrals. Okay, so start out by reminding ourselves of the properties of the exponential functions. So you can see on this graph that the two functions log of x and e to the x are inverses of each other. Let's see. Here we go. Okay, so first things first, if you remember, based on this notation, ln x means the natural log of x. And at the same time, though, keep in mind that it means the same thing as the log to base e of x. Okay, so every log has a base. And for all the other logs, we use the word log. Okay, and we specify the base. This is the only one that gets its own separate name. That shows you how important it really is. Okay, so when the base is e, and remember e is a constant, which is approximately equal to 2.7828, that base is known as the natural log. So therefore, it stands to reason that if f of x is the log of x, the natural log of x, that is, its inverse would have to be e to the x. And so you can see by the graphs, as we saw in the previous section, there will be symmetry around the line y equals x because the two are inverses of each other. Okay. And of course, that implies that the domain of one is the range of the other and vice versa, since they are inverses. And here they're proving it to us. Let's just quickly run through this. If we choose f of x to be the log of x, and f inverse of x is e to the x, we can prove that they are in fact inverses. Remember how that works. It's a two-step process. All right. So in other words, we have to show that f of f inverse of x is equal to x. And in addition to that, f inverse of f of x is also x. All right, so we can do that right now. So first, what is the value of f inverse of x? What you're going to do is take your f of x, which is log of x, and replace the x with f of x. F inverse, rather. Okay, and so then we have log the x, and by definition, this is equal to x. Okay, and then we do the opposite. We have f inverse of f of x. So the f inverse is e to the x. We're going to have e to the f of x, e to the log of x. And again, by definition, this is equal to x. All right, so we just got through proving that f of x equals log of x, f inverse of x equals e to the x. They are, in fact, inverses of each other. All right, let's see. Oh, yes. And so these two properties, these are two that you should keep in mind whenever you're working on problems from this area. These are two identities that will help you enormously simplifying your results. So if anything, like if you have a list of facts that you want to memorize or charts or tables, let's say, this definitely belongs in that list. Now, by the way, this is true for logs of all bases. For example, the log base 2 of 2 to the third is the same thing as, well, it's just 2/3, which is 8. But it's true for all of them. So anyway, log e to the x equals x. because remember they're inverse functions, so what they're effectively doing is canceling each other out. So it's no different than taking the square root of x squared. It's the exact same principle. All right, so here, for example, they want us to solve for x when 7 equals e to the x plus 1. So they have a graph here to help us visualize what's happening. So y equals e to the x plus 1 is the gray line, and then, or the gray curve. Y equals 7 is the black line, and you can see where they cross. That would be our solution. Now, here's how you can do this algebraically. We're going to take the natural log of both sides of this equation. All right, so that means if I do that, now remember, we already have this up here. Log e to the x is x. In general, we could rewrite this as log e to the f of x is f of x, and then e to the log of f of x is f of x. Okay, so in other words, this is not just restricted to x itself. Any function of x, log e to the f of x is f of x, and log e to the log x. Oh, actually, I should have written this. Sorry, this should have been log of f of x. Okay, all right, so that being the case down here, you'll see that log 7 equals e to the x plus, just x plus 1. Okay, again, think of the log and the e as canceling each other out, and therefore, and this is just a constant. They point out in the slides what it's equal to. You can go to your calculator and solve for this very easily. It's about 0.9459. Okay, or normally you would just leave it as log 7 minus 1, unless you need the exact value like that. Okay. And okay, so they're double checking it here. Now here's some properties that we need to know about exponential functions, and these follow along exactly with what we would get with any other real numbers. For example, e to the a times e to the b is e to the a plus b. E to the a over e to the b is e to the a minus b. So let's say you had okay, and then here you'd have e squared over, let's say, e to the third. Okay, and of course, this is true for all real numbers. If you could replace the e with 2 or x, it doesn't make any difference. Now the domain, now look at this graph of e to the x. It's a very interesting graph because you can see it actually has an asymptote. The horizontal axis is an asymptote. And so the function never quite reaches the horizontal axis. But the domain is the entire real number line. Okay, there's no value of x that could cause division by 0 or cause this to be an imaginary result. And at the same time, though, because the horizontal axis is an asymptote, the range, if you notice, is 0 up to infinity, but not including 0. Because again, the horizontal axis is an asymptote. So it's everything from 0, not including the 0, up to infinity. And just by the graph, you can see that it is continuous, increasing, and one-to-one. So in other words, if I took the first derivative, you could see that it is always positive. And of course, you can see that it is one to one. No matter how much I increase x, the function always increases. And therefore, it must have an inverse, which we know to be the log of x. We also know the function is concave upward. Now, that's something we haven't really talked about, concavity. Um, that just simply means that the slope itself is not only positive, but it's increasing as x increases. This is something you'll see more of in Calc 2, by the way. And the limit as x goes to negative infinity is clearly zero, again, because that's a horizontal asymptote. But as x increases to positive infinity, the function converges to infinity. In other words, it does not have any upper limit. All right, now derivatives. Now, as it turns out, derivatives with these two types of functions are actually very straightforward. If you're taking the derivative of e to the x, it's just e to the x. It's so simple. If you have a function of x, though, like u here, as you can see, then it's a little bit more complicated, but not much. The derivative of e to the u, where u is a function of x, is e to the u du dx. So let's look at some quick examples here. So of course, u would be the 2x minus 1. Du dx is 2. So therefore, it'll simply be e to the 2x minus 1 minus 2, or what you usually do in these cases is you write the 2 first. And that's it. We're done. Okay. So here's the thing, though. This is the part we have to be careful with right here. We do need the derivative of u in order to get a result. How about this one? Right. So it's e to the minus 3 over x. So of course the u is minus 3 over x, or it might be easier to write it like this. So therefore du dx will be positive 3x to the minus 2. So e to the u du dx becomes e to the minus 3x to the minus 1 times 3x to the minus 2. Bit of a mess, but we can straighten it out a little bit. All right. Now, what they did, you can see they simplified it a little bit differently. This is equivalent to 3e to the minus. And by the way, they're also rewriting this term as 3 over x, because of course it's the same thing. And then they're putting the x squared in the denominator. Again, it's the same thing. Okay, so this is how they wrote it. 3e to the minus 3 over x, all divided by x squared. Okay, I guess they figured it looks neater that way. Now here, now this one, of course, is a product rule. So of course, remember how that works. So in this case, this is our f of x, this is our g of x. F prime of x is simply 2x. G prime of x is e to the x. Okay, remember, that's our simple case. The derivative of just plain e to the x is just e to the x. Okay. We had, oh, it was in the slides right there, this one. Okay. Just, just a quick reminder. Okay, so now we make our substitutions. X squared, e to the x, plus e to the x, 2x. All right. Oh, I see what they did. They factored out the x as well. Okay. And we have the same thing, of course. All right. Now this last one, of course, involves a quotient rule. So this time we have, now remember how this quotient rule works. Actually, I'm going to run out of room. Let me move that. Okay. So in this case, f of x is this piece, and g of x is e to the x plus 1. Then f prime of x is, now in this case, u is 3x, which means du dx is 3. So this reduces to 3e to the 3x. Okay, and then g prime of x is simply e to the x because, um, oh, I didn't draw this correctly, did I? This should be e to the x plus 1, sorry. That's not part of the exponent. Because of course the derivative of e to the x is e to the x, but the derivative of 1 is 0. So these are the derivatives that we need. Okay. So yeah, let's just take a step back here and look at this one more time. All right. So that way, we know where this comes from. This one is very straightforward. So now we just do some substitution. All right, let me just quickly write down the values again, so we don't lose them. F of x is e to the 3x. G of x is x e to the x plus 1. F prime of x is 3e to the 3x. And g prime of x is simply e to the x. So now we can make our substitutions. All right, and then we, of course, simplified a little bit. You can see, for example, both of these terms contain an e to the 3x. So let's factor that out. Yeah, that's right. All right. So we'll reduce that to these two add up to 2e to the x plus 3. And then we end up with e to the x plus 1 squared in the denominator. All right. Now, they may have done this a little bit differently. E to the 3x. Oh, no. Yeah. No, they did it the same way. Okay, great. All right. So what's next? Now, it says find an equation of the tangent line to the graph. And of course, we know this means take the first derivative at the point 1, comma 3. All right, so let us consider now f prime of x, clearly the 2 has a derivative of 0. What's the derivative of e to the 1 minus x? So this is going to be e to the u du dx, e to the 1 minus x times negative 1, or so that means the derivative of this function is, and then we're supposed to evaluate it where the point is 1 comma 3. So in other words, if this is f prime of x, it's f prime of 1. Now anything where the 0 power is just 1, so the final answer is negative 1. All right, so hopefully, yeah, negative 1 right there. So this is what the function looks like at that point. The slope is exactly negative 1. And then what they're doing is going ahead and showing how to solve for the actual equation of that tangent line. We already know the slope is negative 1, and we know one of the points. So we're going to use this point slope form to find this equation. So again, we know that the slope is negative 1, and one point is 1, 3. And so it's easy to find this equation. Okay, so you might remember this from the very, very beginning of pre-calc. Y minus y1 is m times x minus x1. This would be our x1. This is y1. So we have y minus 3 equals negative 1, x minus 1. All right. So in order to get this into the form y equals mx plus b, we'll add the 3 to both sides. And that's our line. All right. And of course, you can see it has a slope of -1 and it has an intercept of 4. Now, see, now we have to work this backwards. We have to learn how to take integrals of e to the x or functions, e to some function of x and the natural log of x. So first things first, the integral of e to the x is very simply, well, it makes sense because if the derivative of e to the x is just e to the x, the integral of e to the x must be e to the x. The only thing that's different is the constant. If we have a function of x, the only difference here is that to have this du, we have to make sure we have du in the integral in order to make this work. We'll see later on with some examples how to do this. Okay. What else do we need to know? Oh, we're going to have some examples. Good. All right. So if u equals 3x plus 1, du dx is 3, and du will be 3 dx. So it's a typical u substitution problem, except that the function itself is an exponential function. And therefore, now, of course, as so often is the case with these u substitution problems, we're very close to having du. We're just not quite there, but since a constant is all that's missing, we can supply it ourselves. You can see we need the 3. So let's rewrite this as 1/3 e to the 3x plus 1, 3 dx. Okay, now, of course, this doesn't change anything. That's the same expression. It has the same value, but now we have 1/3 e to the u du. What do you know? And we already know that this equals, and of course, since we define u to be 3x plus 1, this is our final answer. All right. So, like I was saying before, these are not terribly, terribly difficult compared to some of the other ones we've seen. Especially the trig ones. The trig ones are always very tricky. But anyway, um, now here's an interesting one. They're going to ask us to do a definite integral. Well, the procedure hasn't changed. It's still based on the fundamental theorem of calculus. So let's try this one. So this time, let's try u equals -x. Du dx is -1. And therefore, du is -dx. We don't have that. We'll need to supply that ourselves. Okay. So what do we have here? Oops. All right. So of course the integral is e to the u, but now because it is a definite integral, we don't need the c. So instead we have, okay, before we continue, it's a definite integral. We change the limits of integration. It's too easy to forget about this. It really is. So the 0 and the 1 refer to x, not u. That's why we have to do this. So when x equals 0, u equals, since u is -x, it's zero. But when x equals one, u becomes negative one. Okay, so with the new limits of integration, we have e to the u du. And of course, as we've seen before, this is going to leave us with e to the u evaluated between 0 and negative 1. And of course, we know that u is equal to, well, actually, no. First, we're going to do this. Negative e to the minus 1 minus e to the 0, negative e to the minus 1 plus 1. Or, of course, you can rewrite it as 1 minus e to the minus 1, or finally 1 minus 1 over e. And that's going to be approximately equal to, if there, so this is approximately equal to 0.6321. All right. And then they're going to show us on the graph what that actually looks like. Okay, so in other words, what they're looking for is the area under that curve, e to the minus x, between 0 and 1. The shaded region is the 0.632. Oh, now this one's a little bit trickier. Let's see what we can do this one. All right, so why don't we try it this way? Let's let u be 1 plus e to the x, then du dx be 0 plus e to the x, or just simply e to the x. And then, of course, that means that du is e to the x dx. So I rewrite this a little bit. Also, I have to change, remember, to change the limits of integration. Um, so when x is 0, u is 1 plus 0, which is 1 plus 1, which is 2. And then when x equals 1, have u equals 1 plus e to the 1, or which is leave it just 1 plus. And of course, that's just a constant. All right. So that means we're going to have all right. So remember, du we recognize is from up here. Wait, where's, oh, here it is. Yes. So du is the numerator, e to the x dx, and then the denominator is u. So we have this result, and of course we've seen this before. That means the result is actually natural log of absolute u evaluated between 2 and 1 plus e. Right? So that's going to leave us with natural log absolute 1 plus e. Now, 1 plus e is guaranteed to be positive, so we can just drop the absolute value signs. And so we ultimately end up. And then if they need the exact value, it's going to be approximately, let's see. 0.6201. All right. Beautiful. And then now this one, ooh, it looks like a linear function, although I'm sure it's not really completely linear. There is a little bit of curvature here, but this is what we end up with. Ah, and what about this one? All right. Let's see. What should we do about you? Well, let's just let it be e to the x, then du dx is e to the x, du is e to the x dx. Okay. And then as far as the limits of integration go, when x equals -1, u equals e to the -1. And then when x equals 0, the upper limit, u equals e to the 0, which is 1. All right, so we can bring all this together. We might want to rewrite it slightly first. It's pretty clear that we do have du here. So we change the limits of integration, and we end up with okay. Now it's been a while since we had to take a trig integral. So remember, I did put together those little tables, which are found in the right space, but I have them open right here. So let's go back and remind ourselves, what is the integral of cosine u? Just in case you haven't memorized it, and that would be sine u. Okay, we don't need the constant because this is a definite integral. And I guess we could look those up in the calculator to find out the exact value. Let's see how they did it. They may have simplified it a little. No, they just did it directly. Okay. Um, that's interesting. Sine 1 minus sine e to the -1. And they went ahead and calculated as approximately 0.482. I'm going to double check that real fast. So sine 1 is approximately 0.4147. Sine e to the -1 about 0.3596. So that looks about right. 0.84147 minus 0.3596. It's about, yeah, that's right. Okay, wonderful. Okay, what else do they have for us? Oh, okay, it's time for some knowledge checks. All right, great. So the first one is All right, now here we're simply solving for x using our understanding of the property of logs and exponential functions. So first, of course, now you want to simplify this as much as possible. And then we can apply the logarithm. Okay, we'll take the log of both sides. And of course, on the left, the log of e raised to any function of x becomes that function of x. So we have 3x equals log 15 over 7. And then, of course, I divide up the 3 from both sides. And there we go. And well, what do you know? It's a. All right, what else? Oh, derivative. All right, now, of course, this one involves a product rule. So again, just as a quick reminder, this gives us and so here we'll let x to the 6th be our f of x, which means that f prime of x, the power rule is 6x to the 5th, and then g of x will be that e to the x. And of course, that means g prime of x is also e to the x. It's so convenient. All right. So anyway, we end up with x to the 6th, e to the x, plus e to the x, 6x to the 5th. And they will probably expect us to factor out the e to the x. Oh, but they won't be satisfied with that. We're going to also factor out the x to the 5th. Yeah, and that's as simple as it's going to get. So that would be x to the 5th, e to the x plus 6. There it is, c. Perfect. All right. So that was a relatively straightforward chapter. Not that it was easy. So we now are ready for 5.5. Bases other than E and applications. Okay, let's see what that's all about. All right, now here's an important definition. What they're basically saying is all of that only applied when we have base E. Okay, what about the other bases? Any other real number, we need to know how to handle those as well. Okay, so what do we do? So we start with this definition, and this is the heart and soul of everything that we're about to do. Okay, in other words, when you take something like a to the x, if you rewrite it as e to the log a times x, then we're applying the exact same rules. Okay, so just keep in mind that this is an identity that you really should be aware of because it'll help you with the problems in WebAssign. Don't forget it, right? Because otherwise, a lot of what we're doing won't make any sense. All right, so for example, all right, well, this is exactly what we were looking at before. A to the 0 was 1. Here we have the product rule for exponents. A to the x times a to the y is a to the x plus y. Here we have the quotient rule for exponents. A over x over a to the y is a to the x minus y. So in other words, for this one, we're adding the exponents, and for this one, we subtract. And then finally, now this is the power rule for exponents. And here, if you notice, It's a to the x times y. Okay, that's the only time that we do that. All right, so here we go. Here's a good example. The half-life of carbon-14 is about 5715 years. Okay, now of course, you've heard of carbon dating. This is how they figure out how old things are. Let's say a new tomb is discovered in Egypt and they find mummies and they want to know how old they are. This is how it's done. By the decay of carbon-14, which is an isotope of carbon-12. The element carbon actually has an atomic weight of 12. Carbon-14 is an isotope which has, if I'm remembering correctly, two extra neutrons attached to it. It's been a while. So a sample contains 1 gram of carbon-14. How much will be left in 10,000 years? So what we're looking at here is something called exponential decay. All right. So we're going to have T is 0 means the present time, and Y is the amount in grams in the sample. 1/2. So this is the model we're going to use. This is how we can decide how much will be present at any given time in the future. And if you notice, it's T, the actual T. Now keep in mind, T0 means today. T1 is next year, T2 is the year after. Okay. So we'll let T is 0 be now, the current time. And so this is our exponential decay model. And they want to know how much will be present in 10,000 years. And yes, what they want you to notice here is that the point of the half-life is that in another 5,715 years, there will be 1/2 of a gram left. Okay. In other words, every 5715 years, the amount of carbon-14 is cut in half. So if that's the case, where would we be in 10,000 years? So it's a very simple matter of replacing the T with 10,000. So they're going to, wow, that was easy. Plug in T equals 10,000. Whatever that number is what we're looking for. Now, clearly, it's going to be less than 1/2 because the exponent is more than 1. All right, let's see what it is. It's approximately, now on the calculator, it's going to turn out to be such a small number that they're going to use scientific notation. It actually shows up in the window as 5.345 e to the minus 6. What does that mean? This is the equivalent to saying this is how most calculators express scientific notation, by the way. And then that means there are 5 leading zeros. That's how much will be left in our sample. Okay. All right. Now they have a graph here, so you can see how this is working. So they've got on the horizontal axis, let me just copy this so you can see it better. The horizontal axis is time in years. So that T variable is in years. And so this is what it looks like. Hmm. That's interesting. I got something different than I did. Let me double check my numbers. Oh, I made a typo. Oh, okay. It's a good thing I double checked. Hold on one second. Yeah, we knew something wasn't right. Yeah, okay, never mind the scientific notation. I accidentally left off the five in this 5715. So yeah, that made a big difference. Unfortunately, so um it's actually approximately 0.2973. That's a lot better. So when you look at that graph, you'll see, yeah, that makes a lot more sense. So after 5,715 years, by definition, there's half of a gram left because that's the half-life. And then after 10,000 years, it's zero point 0.3. So you notice that curve is not getting steeper, it's actually getting flatter. So the amount of carbon falls off very slowly as we get further into the future. Okay. Another definition that we need to know. And again, this is so that the rules that we're about to look at make sense. In fact, we should probably gather them up into a single location. In fact, I'll tell you what, maybe I'll make another chart. This one, I think we're going to need this one. Hold on one second. Okay, so we'll need the one we had a few minutes ago. Well, we'll start with this one. And of course, I'll post this in bright space so you can print it out if you need it. And we previously saw at the beginning of this section, here we go. We'll need this one. Okay. Now, by the way, this what's interesting about this definition is that this actually is very helpful when you're using your calculator to solve for logs with bases that are not on the calculator. In other words, the calculator only has base 10 and base e. What do you do about the other ones? Well, this formula will help you do that. So let me just show you a quick example of that. The reason why this is so helpful, among many other reasons, is because it lets us calculate logs where the base is not actually on the calculator. So for example, what if I needed to know the log base 2 of 32? Well, there's no log 2 in this calculator. It has 10 and it has the natural log, and that's it. So it turns out what I can do is rewrite it as let A be 2, X is 32. I'm going to rewrite it as like this. And if you plug that into your calculator, you'll see that it's 5, which is correct. The reason why we know that it's 5 is because 2 to the 5th is 32. So this is correct. But again, the calculator doesn't have log 2. Well, oh, actually, it does, but it's not. I shouldn't say that. It's not on the main. If you look at the main keyboard there, you don't see it there. But it turns out it's hiding in one of the menus. So let's say you wanted to use the menu instead of this relationship. What you have to do is this. All right, so here's what you have to do. And if you didn't know this was here, you were never going to find any numbers. Um, math, and then, oops, if you scroll down to A, it says log base. Okay, and then you hit enter, of course. And if you notice, it says log, and it's got two blanks. What you're going to do is enter the 2 and the 32, and then hit enter, and you get your 5. So this calculator, I'm telling you, if you don't use it all the time, there's so many wonderful things built in here you probably didn't even know about. And this is a classic example of that. So, but having said that, let's just say for some reason you didn't know about this special feature. This identity would also get you the result you're looking for. So it's good to be aware of multiple ways of getting to the same result. All right, good. So I'm going to leave these here. I'm going to post these later on because we're going to need them for the MindTap assignments, of course. And also, this will help us understand the logic behind the derivatives and integrals that we're about to introduce. Okay, where are we? Here we go. Now here's some of the properties of logs that, by the way, these are the same for any base that you choose. Some books, when it doesn't matter what base you're using, they leave off the base altogether. You do run into that sometimes. And also this applies to natural logs, but the point of it is that number one, the log to any base of 1 is 0. Number two, the log of a product is the sum of the logs. Okay, you notice how log A, whatever A is, of X, Y, equals the sum of the individual logs, as long as they all have the same base. That's the important thing. If not, you cannot directly combine them. The log of ax to the n is n log ax. Now, this one is going to really be hugely helpful in simplifying results as we're going along. We may find that we're trying to integrate x to the n or something like that, log to x to the n. But often we can simplify results with this one. This is really one of the most useful, helpful. And then finally, the log of the ratio is equal to the difference of the two logs. Okay. And oh, and here's another one. This is good. If f of x is a to the x, this one I think belongs on our list. If f of x is a to the x, then log a of x these are inverses. Of course, you can see that if I replace the a with an e, you already knew this. E to the x, natural log x are inverses of each other. But the point of this is that it doesn't matter what the base is, it's still the same for every real number. Um, oh man, these are some really important ones. All right, let's add these to the list. So in other words, if you have y equals a to the x, we can rewrite it as x equals log a of y. And that's again a consequence of them being inverses. And then here, A to log A of x for x greater than 0 equals x. Okay. And then finally, this one is also true. And let's see. Let me just make sure this one has page numbers. And if you think in terms of A being equal to E, A is, remember, a real number. One of the implications of this is that I'm going to add these to today's notes. Based on what you're seeing here, A log AX. Actually, I'll copy these over here. In terms of natural logs, where the base is E instead of A, this is what these imply. By the way, this if and only if, sometimes you see it written in math with this special double arrow. It means the causality goes both ways. Okay. Um, number two, so in other words, if y equals e to the x, that implies that x equals log y, and vice versa. For number two, e to the log x equals x, as long as x is positive, because we have to stay in the domain of its function. The domain of the log of x is 0 up to infinity without including the 0. And then three, this last one implies that log e to the x is also x. So in terms of e, again, you can see why, because e raised to the log of x, they're inverse functions, therefore we end up with x. Log e to the x, they're inverse functions, therefore we end up with x. These two in particular, I find to be particularly useful. Again, in simplifying equations that we're trying to solve for, or even better yet, in simplifying integrals. That's often the reason why we're doing this. Let's see, for common logs. So in other words, they're saying if A happened to be 10, which makes a common log, then y equals 10 to the x implies that x equals log 10 of y. Okay, we're not going to see that nearly as often as the natural logs. So here's our first application of this. So what do we do? I mean, wow, this is very strange. What we can do is take the log to base 3 of both sides. The log of base 3. Which we're certainly allowed to do. Okay, now, if you come up here, you'll see that log a of a to the x, oh, there it is, equals x. How do you like that? So that implies that the left-hand side is simply x. Now, over here, what we can do is this. 1 over 81 turns out to be 3 to the minus 4th power. All right, so in other words, 3 to the fourth is 81, which means 1 over 81 must be 3 to the minus fourth, and that means that x equals negative 4. And if you're not sure, I mean, you say, well, let's prove that. Um, the original equation was this. Plug in the negative 4 into your calculator, or the decimal equivalent of it. All right. How about this one? Now, with this one, um, we're trying to reproduce this result right here. Let's copy this down here. Oh, I just realized I'm in the wrong document. Um, okay, hold on. Here we go. Yeah, I didn't really say anything, did I? No, this is good. All right. So in other words, we want to write it like this. So in this case, A is 2. So you've got 2, so log 2 of x equals 2 to the minus 4. And according to this principle, this is just x. Okay. That's how that's done. So, like I said, these are going to be hugely important, these three, especially these last two. Not that these aren't important, they certainly are. Now, we already know how to take the derivative and the integral of functions involving e to the x or natural log of x. What about when the base is not e? What do we do now? Well, this is going to make things a little bit messier. In fact, I'll tell you what, I think we should probably put these on that list. We're going to need them. You see, this is a lot to remember. And as you'd imagine, later on, we'll have an equivalent chart with intervals. Okay. So yes, it does get a little bit messier. Now, keep in mind, if A was equal to E, you can see how things would simplify to what we're used to seeing here. For example, in this first case, log E is just 1, and then you'd have E to the X. That kind of thing. So it's only messy. It's messier because of the fact that we're not using E. Okay. So let's try some examples. Y equals 2 to the X. What's the derivative? All right, let's try that. Now, up until we got into this chapter, we wouldn't have had no idea how to do that. Okay, so we have some new techniques available to us to make things a lot simpler. Okay, so which rule are we looking at? Let's go back here. Looks like it's the first one. Okay. Derivative of a to the x is log a to the x. All right. Yes, a to the x log a. So therefore, this one must be log 2 to the x. Okay. Yeah, it's right there. Okay. Ooh, what about this one? So it's 2 to the, it's actually a function of x now. That puts it in this category over here, a to the u. Okay. So we need this one on the right. Um, hold on. Yes. Okay. So now we're good. So once again, it's a to the u log a um, du dx. So if we let u be 3x, u dx will be 3. So d1 dx in this case is now, oh, and of course, a is 2. 2 to the u log 2. And du dx is 3. Of course, we have a definition of u equals 3x. Okay, so it ultimately ends up being 2 to the 3x log 2 times 3. Yeah, so they wrote it as 3 log 2. Well, that makes sense because they're both constants. I can see why they did that. That looks nice. 3 log 2, 2 to the 3x. Oh, oh my God. Now we're getting into some very deep waters because we have trig functions involved. All right, how does this work? Now, keep in mind, this is the log of cosine of x. This is not a product. So if we go back to our table, what are we going to find out? We're looking for the log to base a of some function of x. Aha, it looks like it's this one. D log a over u. Sorry, D log a of u. Did I write that correctly? No, I made a mess out of it. It's log base a of u. That's better. A dx. No, wait a minute. Yes, dx. Hold on. I wrote the wrong thing down here. This is dx. That's better. All right, now we have 1 over log a u. This is a product, by the way, and then du dx. Okay, great. So in this case, the u would be the cosine of x. And if you remember from way, way back, a few weeks ago, on my table here of basic rules of differentiation, the derivative of the cosine is the negative sign. Okay. And then a, of course, in this case is 10. So here's what we end up with. 1 over log 10, which is log natural log 10. No, I wrote it again. U is cosine x. U dx is minus sine x. Okay, so that should do it. And they, you know what they did? Those clever guys, they went ahead and replaced sine x over cosine x with tangent x. Okay, so of course it's the same thing. So one of those identities that you really should have memorized is that the sine of x, cosine of x is the tangent of x. And that's how they left it. Okay. Okay, so this is the next example. Let's see what they have for us. Okay, so I think the idea here is that they want us to simplify this before we get started. Okay, because we're going to take a derivative and it's going to be an incredibly messy one the way it's written. So they want us to take advantage of the rules that we learned earlier or reviewed earlier. And so, in other words, because this is the log of ratio, we can turn it into a difference. We could do it like this, for example. Okay, based on the properties of logarithms, which tell us that the log, no matter what the base is of x over y, is the same thing as log ax minus log ay. All right. And then we can simplify it maybe just a little bit more. In other words, I was thinking about simplifying the square root. And the reason for doing that is because if you remember, the log, no matter what the base is, a to the x to the n power is simply n log x. So I'm going to rewrite this as 1/2 log base 3 of x minus log base 3 of 2x plus 5. Now we can start to apply the derivative rules that we just introduced a little while ago. So we might as well do this in two pieces. We'll start with the first one. So the trick is to look at this chart and see which one it most resembles. Okay, so it's the log to base A of X only. So it looks like this third one. Okay, so that one will be the log, 1 over log A of X, times X. All right, so let's just copy this one more time. Log AX is equal to 1 over log A times X. Oh, sorry, not log, natural log. I copied the wrong thing. Natural log AX. Much better. So based on that rule, look, what do we have? That implies that this one will be 1/2 times 1 over natural log 3 times X, or 1 over 2 log 3 times X. What about the second one? This piece right here. All right, let's see. We're looking for d dy, d dx of log 3 of 2x plus 5. Now, this is clearly a function of x that we're looking at. So what we're looking for is this. We have the log to base a of a function of x, and that appears number 4. That looks like the right one. All right, so let's see what that does for this one. So that means this is our u, this is a. So we've got 1 over log 3, natural log 3 times u, which is 2x plus 5. Now du dx would just be 2. Or, of course, we could simply rewrite it as move the 2 to the numerator. All right, so we got both halves. Now we just bring them together. So here, this is the original function. All right. So the derivative must be, so the first part we already found, the answer is 1 over 2 log 3x. Actually, we should probably rewrite this a little cleaner. We want to make it very clear that this is not the log of 3x, it's the log of 3 times x. So let's write it as in a slightly different way. There it is. Yeah, so even here, it's probably better to write it like this. 1 over 2 times log 3 times x. That's better. And then, now remember, the original function we were subtracting, so the derivative in the second case is 2 over log 3 times 2x plus 5. All right, so that should do it. It's, we can certainly simplify it, but that's the final result. let's see. They love to simplify it. Now you see what they did. Well, we can leave it like this. This is fine. Let's see, they've got it here. 1 over 2 log 3x minus 2 over log 3, 2x plus 5, which is fine. We just didn't simplify it as much as they did. Okay. Now we're gonna integrate functions that have bases other than e. Okay, so we haven't done this yet. So we've got the integral of a to the x. As a matter of fact, I'm going to go back and get my chart that I've been working on and add this to the list because we definitely need it. Okay. So when we're integrating a to the x dx, this is the final result. So if we, for example, want the integral of 2 to the x, we can use that property that we just saw. And you can see that in this case, a is 2. We just end up with 1 over log 2 times 2 to the x plus c. Or here we write it, of course, as 2 to the x over log 2 plus c. All right, great. What other rules? See, now these rules we know. We know these very well. But all right, let's just copy them anyway. So they're basically trying to show you how they got to these points. We know this one. This is the power rule for differentiation. And this is the general power rule where u is a function of x. These we know very well. So now, oh, okay. So here's some interesting results. We know that, now that's interesting. E to the E, I wonder if that's a typo. Um, no, I guess, no, it's not because that's a constant. All right, so that's equal to 0. The derivative, as we know, e to the x is simply e to the x. Now, this one is a little bit different. What happened here? So now keep in mind that e is a constant. So that means we're just simply using the power rule. All right. So let's apply that here. So in other words, you have, let this be your end. So you're going to end up with e x to the e minus 1. So that's where this came from. It looks very strange, doesn't it? But that's exactly right, just because of the fact that e is a constant. Now look at this one. Y equals x to the x. So when you see a really bizarre one like that, often the only thing we can realistically do is use logarithms. They're really challenging us with these. So what we're going to do is this. We're going to take the log of both sides, which we know the derivative of actually, sorry, the log to base, any base really. Now, when we differentiate it, we're going to use implicit differentiation, which we've seen before. So we use implicit differentiation. Because the function is not y equals some function of x, it's log y. So that means we have to use implicit differentiation. And we've seen this before, but when you take the log, the derivative like this, it ends up being y prime over y. Okay, that's an important detail. So when you use implicit differentiation with logs like this is the result for the y's. Now for the x's, we're just going to have a standard product rule. Okay, so we're going to have on the left-hand side of this equation y prime over y. On the right-hand side, we're going to apply the product rule to x log x. So in other words, so for differentiating x log x, what do we get? Well, first of all, f of x is x, f prime of x is 1, g of x is log x, and of course, g prime of x is 1 over x. Okay. So then when we plug these in to the product rule formula, we have let's see, x, 1 over x, plus log x times 1. So we have 1 plus log x. So the left-hand side of this equation, when we bring all this together, we have y prime over y, 1 plus log x. Now we multiply both sides by y. And then y equals, originally y was defined as x to the x. So I don't think there's any way to simplify this. All right, x to the x times 1 plus log x. Beautiful. But yeah, I mean, like that requires us to recognize that we needed to use implicit differentiation because of the logarithm. And it also required us to notice in the first place that we can use logarithms and apply them to both sides. Okay. All right, now applications. Now, here's something we definitely did in pre-calc. This is the formula for the future value of a sum. Okay. So what is this all about? Basically, what this is telling us is if we put a sum of money in the bank today, how much will it be worth in the future? Okay. This is the formula. So here's the components of this formula. A is the future value of a sum. P is the principal, which is the sum that we're referring to. In other words, this is how much we started out with. R is the rate of interest. In this case, the annual rate of interest. Now, N is an interesting variable. N is the number of times per year that interest is credited to the investor. In other words, in more formal terminology, it's the compounding frequency. Okay, let's just make that a little bigger. So now, in other words, let's say that interest is being paid 4 times a year. With quarterly compounding, meaning 4 times a year, n equals 4. So that's all it means. Anyway, so if I start out with P dollars and I invest in the bank for n periods, which don't have to be years, by the way, and R is the annual rate of interest, this will tell me how much I'll have in the bank at some point in the future. So I think they probably have a bunch of examples here. Yes. So here's one. Let's do one or two of them, just to get some practice. We start with $1,000 at 8%. All right. So again, P is 1,000. That's how much we put in the bank now. And telling us that the interest is 8%. Now it appears they didn't explicitly say so, so it looks like this is for 1 year. They really should have mentioned that, but they did not. So in this formula, we have 1 year. R is 8%. Here we go. Actually, I just noticed the way they wrote this formula, it looks like it's based on the assumption of 1 year. This is not the most general expression of this formula. I'm a little bit not happy about the way they did this, but we're assuming that this is 1 year. Okay, that'll do. If we had more years, we would need another variable in this formula. But all right, let's run with this. So they want us to calculate the future value under different assumptions about n. And if you look at the table, they go from 1, which is annual, 2, which is semi-annual, 4 is quarterly, 12 is monthly, and 365 is daily. So I'll tell you what, let's try n equals 2, just to get some practice. So what you're basically doing here is multiplying 1,000 times 1.04 squared. And of course, whatever answer you get, you'll round it to dollars and cents. So that's equal to oh, wait a minute. $1,081.60. Now, if we increase that to quarterly, and this is the interesting part, what happens if we increase that to quarterly? So you've got half the amount of interest being paid twice as often. That's what essentially this means. So you actually now have 1,000 times 1.02 to the fourth power. And so let's see what happens now. 1082.43. Now, since we started out with $1,000, that means here the interest that we earned is 81.60. And down here, the interest is, of course, 82.43. So what happens is that as you keep increasing the compounding frequency, the n the interest also increases, so that the future value increases. In other words, your balance in the bank can grow more rapidly. And in the chart in the here you can see, now it's not a huge increase by any means. You can see in the top, we have $80, 81.60, 82.43, 83, and then finally 83.28. So you can see that it's increasing at a decreasing rate. And between 12 and 365, it only went up by another 28 cents. So it turns out this function actually has a limit. So this is a very important result in finance. If I take the limit of this as n goes to infinity, I'm going to get a very special result. You'll recognize right away what this is all about. It reduces to e to the r. So that means that a would be simply p times e to the r. And in this example, with an 8% interest rate, the future value would be 1083.29. So if you look at that chart with daily compounding, it was, yeah. So in other words, one more penny. You can see now when n goes to infinity, by the way, we say that this is continuous compounding. For all the cases when n is finite, we say that this is discrete compounding. So with continuous compounding, the balance in bank account is experiencing exponential growth. So that's the tie-in with what we've been doing right there. In the limiting case, we end up with this. And that's because you may not have ever seen this definition before. In general, these are two limits that they usually like to save until this part of the course. There's two equivalent definitions, each of which will give us E. Okay? So in other words, this is how E is formally defined. You've seen it before, but now you understand where it came from. It's a limit. That's all it is. This proves to be a very important result, by the way. All right, so don't forget about that. All right, anyway, so here's what they're doing. They want you to see that if you were to calculate this ratio for increasing values of x, you can see it's getting very close because remember, E is approximately equal to, if you go to your calculator, 2.718, 28, 1828, and it goes on and on forever. Okay, so in other words, if you keep increasing x in this formula, you can see that it's getting very, very close to E. So because of that, like I just showed you, if you use this formula, if you take the limit as n goes to infinity, you do end up with PE to the R power as your future value formula. And yes, we just got through doing this. They anticipated what I did. The future value would be 1083.29. And yes, they do remind us that this is called continuous compounding. So here, they didn't actually mention that this one is discrete compounding, but that's okay. Because the word discrete just means finite, a finite number of compounding periods. All right, so here's one where we have $2,500 is put into an account that pays a rate of 5% per year, and the compounding is quarterly, which means n equals 4. Oh, here's the general formula. You see what they've done? They've added the t that I was talking about before. Notice how before it was missing. Now we put in the t because this is not a 1 year investment, it's a 5 year investment. So I'm glad they did that. So you can see that we have to be told here that this is a 5 year investment. So if you plug in all those numbers, you'll see that you end up with 320509. And since we started out with $2,500, that means the interest must be 320509 minus $2,500. That's 70509. Okay, beautiful. And then what they've done is they've increased it to 12 times a year. And if you notice, the interest went up 70840. And then they did it again with a continuously compounded rate. And that brought it all the way up to 321006. And again, you notice there's a T here now. This is not a 1 year investment, it's 5 years. We do need that T in there. All right. So now here's an interesting case. Y equals 3 to the 8x power. Now it does say use logarithmic differentiation. We now know what that means. Let's get that set up. 3 to the 8x. Now, obviously, we're going to need one of those special properties that we just saw. So in a minute, we're probably going to have to look at that chart again. All right, so first things first, we take the log of both sides. And then we use implicit differentiation. Now, keep in mind here, this was not a terribly complicated case because this actually could be rewritten as 8 log 3 times x. And so the derivative is just going to be 8 log 3. And then y itself, remember, we originally defined it as 3 to the 8x. And then we're done. That would be D. Now, of course, they did tell us to use logarithmic differentiation. If they didn't tell us that, we could have used one of our rules. We've got a constant raised to a function of x. Let's see which one this is. All right, I know it's back here. Constant raised to a function of x. Now there's this one right here. So I'll just take a quick picture of it and copy it down there. All right, so this is just imagine we decided to go down this path. We have a first, it was y equals 3 to the 8x. So that means a would have been 3, u would have been 8x, and du dx would have been 8. So this would have brought us to log a to the u, and do dx, which is 8. Okay, so even though it's written slightly differently, in a different order, you can see it's the same thing. I could just rewrite it as 8 log 3, 3 to the 8x. So as is so often the case, there's more than one way to get to the same result. So we have a rule that lets us do it directly, but you can see that we also could use the logarithmic differentiation. All right, what else do they have for us? Oh, okay. Where they're asking for continuous compounding. Beautiful. That's the easiest case mathematically, I think. All right, here we go. All right, so they're telling us that we have 25 years. Um, Initial deposit is 2,500, R is 0.07. The formula for continuous compounding is PE to the RT power, which means 2,500 E to the 0.07 times 25. So that exponent is 25 times 0.07 is 1.75. E to the 1.75 is approximately equal to 5.75, 46. That's probably good enough because we only need dollars and cents. 14,386.51. And again, remember, this would be rounded to dollars and cents. The bank is not going to give you fractions of a cent. Okay, here we go. Let's see what they've got. Of course, it's B. Beautiful. All right. So that was 5.5. Now, you're probably scared about what might be in 5, 6, and 7. It is getting very intense. It definitely is. So let me just quickly show you what these two look like. 5, 6 is where we start to look at. Ooh. Now, this is actually one of the most important parts of not just the chapter, but the entire course, because it turns out that when you're taking limits, there are certain situations we run into where we end up with something bizarre like 0 divided by 0, or maybe infinity divided by infinity. And it turns out that in spite of this, there's an easy way to get around that problem. And that way is something called L'Hopital's rule. It's a very powerful result that will make our life a lot easier when we're calculating limits. Of horrendously difficult problem of functions. So this is going to be a huge deal. We're going to pay extra special attention to this because you'll need it all the time in Calc 2. So that's where we're going. We're going to say, well, wait a minute, what happened? We're getting these very strange results. What can we do about it? Well, now we're going to find out. All right. So anyway, I think we'll knock it off today. We've had a very long marathon session, and next time when we meet, we'll start looking at L'Hopital's rule. So I'll see you then.